Hi there, and welcome to Telefunken. Today, we're going to be talking about the ARP Odyssey, the various test point locations, and pointing out and addressing some errors in the service manual. Before we get started, I want to give a shout out to a couple of other YouTubers. First of all, SynthChaser at synthchaser.com. SynthChaser is an undisputed guru of ARP synthesizers and has a terrific series of videos on his channel illustrating their servicing. I'd also like to give a shout out to Alex Ball. If you haven't seen his documentary Electromotive, The Story of ARP, you should check that out on his channel. And he's been kind enough to allow me to include a couple of snippets from his video On the Wire, which features the ARP Odyssey, in the introduction to the video that you've just seen. Throughout this video, we'll be referring to the ARP Odyssey service manual. The manual for the Odyssey can be found online, and it covers models 2800 to 2823, which are the Mark 1s, 2s, and 3s. Included within the manual is a circuit description, which is very important and I would recommend reading prior to any service of your instrument. There are schematics and PCB layout diagrams for the individual boards, as well as helpful interconnect diagrams. The manual contains trim procedures or calibration instructions, as well as descriptions and a table listing the results that one should obtain when evaluating the various test points in the instrument. It also contains a fairly complete parts list. As good as it is, the manual falls short in a number of areas. The versions available online are old scans with very low resolution, making the schematics and the PCB layouts very difficult to read. In addition, the service manual does not include any filter schematics or the schematic for the PPC control, and most importantly, the manual does not describe the specific location of the individual test points. Some of the test point descriptions and the descriptions of the expected results that one would obtain evaluating the various test points are also described in error. There are also errors on the PCBs that actually have deigned to include test point locations on them, such as PCB C2, which doesn't match up with a description of the test points in the service manual. So in this video, we're going to address these deficiencies and describe exactly where you can find all of the test points, what kinds of signals you should be able to see when evaluating a functioning synthesizer, and hopefully this is both helpful and entertaining. Before we get started, you'll see that I have the PCBs from the Odyssey arranged in a wooden jig for servicing. This allows me to gain access to both sides of the PCB, including the component side, which normally would be in between the PCB and the metal chassis. This isn't necessary in order to evaluate the test points, as you'll see in this video. So we have the Odyssey installed in this wooden jig, which allows us to connect the power to the power supply and power it up and evaluate its performance with all of the circuit boards powered up and gaining access to both sides of them, both the foil side and the component side, which is obviously the other side of the assembly. Because of the arrangement of the various connectors, however, there are a number of things which remain disconnected in this setup, and they include the PPC control, proportional pitch control assembly is disconnected here. The CV gate and trigger in and out jacks on the back of the synthesizer are disconnected. The portamento circuitry, the foot pedal circuitry, is disconnected. I have connected the in and the output jacks and the additional signal input jack to the PCB because that connector is quite flexible and it makes the distance easily. But given that a number of these things are disconnected, we need to ensure that we're taking this into account as we go through the keyboard and assess its function or its performance or lack thereof. And one of the things that we need to be mindful of is that the CV generated in board A actually leaves board A and goes to some of the jacks on the rear panel and then returns to board A before going through the rest of the synthesizer and generating sound. And so in order to account for that, I have put a put a jumper here between pin 2 and 3 right here of this connector, which is J4 on board A. And this is the connector where the CV signal actually leaves the board. In addition, we're going to want to generate CV, and that requires the use of the keyboard, which of course we've disconnected, and it would be connected here at J2 on board A. The keyboard is just leaning to the side here, and when I need to use it to assess the function of board A, I'll be plugging it in and pressing the appropriate keys. A challenge in the service manual, there are a number, but one of them is that the test points are not terribly well documented. In some cases, they actually appear and are labeled on the individual circuit boards, but in other cases, they are not. To add a certain amount of confusion to the matter, there's also different versions of each of these circuit boards. There's board A1 and board A2. We happen to have A2 here, board B1 and B2, and C1 and C2, and so on. So we need to be mindful of the differences in the circuitry on the different boards and make sure that we're paying attention to the appropriate sections of the service manual, which covers the ARP Odyssey 1, 2, and 3. Without further ado, we will use a variac to power up the instrument and assess what's happening with the very first test point. Okay, the power is on, and I have connected the keyboard to the appropriate jack, J2, and connected my voltometer set to DC volts to test point 1, which is pin 5 on J2, which is connected to, I believe it's pin 7 of the ICZ2. What we're supposed to do is find that with no keys being pressed, we should have 0 volts. And in this case, we're measuring 25 millivolts. And with both high C and low C held, we should be measuring 3 volts. So with high C, we see a very minor change. And with low C, we see that we're at 3 volts. And so notwithstanding that these values are slightly different than what's indicated in the service manual, I would suggest that the keyboard is indeed generating control voltages, and they're of the appropriate magnitude, notwithstanding that the baseline voltage is 25 millivolts instead of 0 volts. And that's something that we can address later. But in the meantime, the keyboard is indeed generating control voltages, and these should be adequate to diagnose the operation of the rest of the instrument. Test point 2 is measuring the control voltage buffer. This is to be measured on pin 1 or 2 of Z4. And this is to be measured depressing and holding low C and depressing and holding high C. So currently we have no keys pressed, and we have connected to a pin which has been conveniently soldered in place by a previous technician at test point 2. And we're going to be using that pin to do our measurements. And so if we depress and hold high C, we should get the equivalent of 0 volts. And we get the same voltage that we had essentially represented with no keys pressed at test point 1. So roughly 27.5 in this case millivolts. And we're looking for 0 volts there. And then with a low C pressed, we should get a positive 3 volts, and we get 2.999 volts. Again, about as close as we're going to get there. So this would suggest that the CV buffer is indeed functioning, and we can move on to test point 3. We're connected to test point 3, and at test point 3, we are to measure the CV memory, and without doing anything, we can already tell that it's functioning, because after depressing and releasing low C, we should be at 3 volts. And so I'll depress it one more time. There we are, 3 volts. And we should be able to release that and see it holding that voltage. Now we do see a modest decrease in voltage, which may need to be addressed. But regardless, we see it very close to that 3 volt level. We're looking for no more than a 20 millivolt change in that voltage over the course of 1 minute. And although it has decreased by 6 millivolts, I would suggest that that's probably performing as it should. The second test at test point 3 is to depress and release high C. And we should be getting essentially 0 volts. And when I do that, I see we have 0.0294 volts or 29.4 millivolts, which is similar to the value that we had previously in the CV buffer, slightly elevated. And if I release the key, we see some relatively minor drift here in this voltage, but it is holding stable within the parameters outlined in the service manual. So I think we can move on to test point 4 and say that the CV memory is functioning as it should. So I have just connected to test point 4, which is pin number 1 on the IC Z2, and there is a lead, or rather a pin that has been soldered there by a previous technician. And what we're supposed to do at test point 4 is depress and release low C, which I will do. And we're looking again for approximately 0 volts. Now we have a slightly elevated voltage here. We've got approximately 80 millivolts, and this should stay stable after releasing the key. It's not quite stable. So again, this might warrant attention later, but it's very close to 0 volts. And the second operation is pressing and releasing high C. I'm pressing it right now, 3.044, and we're looking for 3 volts. And again, so this is ballpark within the range of function, and I would suggest that this part of the synthesizer is working more or less properly. The next test point is test point 5 on board A, and that is the gate bus, and that is at J2-1, pin 1 on jack 2, and you can see I have connected my multimeter probe, clipped it to pin 1 on J2, and with all keys up, we're supposed to be getting a reading of 15 volts, and that's exactly what we're getting. If we depress any key, that should be reduced to approximately 10 volts, and it's coming down to 10.8 or so. 10.8 or so when we depress any key, and slight differences in voltage when we press different keys, and that could be due to the fact that some of the resistors on the keyboard assembly, which determine the reduction in gate bus voltage, may have slightly different values. These are not precision resistors, and this does not have to be a precision voltage because all it does is turn on the gate. So this appears to be functioning as it should, and we'll move on to test point 6, the memory gate. We're connected to test point 6, and with all keys up, we're to be looking for a voltage of approximately minus 13 volts, and indeed we have minus 13.6. And if we depress any key, we should get approximately 15 volts, and indeed we get 14.95. And so the memory gate function appears to be working. So the next test point is test point 7, and this is the gate output, and we are connected to J4, pin 4 on J4, and we are looking for essentially 0 volts or close to with all keys up, and we have negative 33 millivolts approximating 0 volts, and then with any key pressed we should be getting approximately positive 12 volts. So I'll press a key, and indeed we get 11.6 volts or so. And again, this part of the keyboard assembly and the gate triggering circuitry appears to be operating as it should. The next signal will require the use of an oscilloscope, and so I'll connect us up to the oscilloscope and go from there. So we're currently connected to the trigger out test point 8, and that is J4 on board A, pin number 1, and this is the trigger out signal. We're looking for a very short signal around 14 volts, plus 14 volts upon the depression of any key. And so you'll see that if I press any key, we see a very brief, and we saw a few triggers there because I slipped, and you'll see a very brief trigger signal that's around 14, 15 volts. And so again, it appears that this function is working as it should. The next test point that is on board A is test point 9, and that is the white noise test point. Both test point 9 and test point 10 are the pin number 1 that is on the interconnect PCB that connects PCB A, B, and C together. The noise signal moves from board A through the rest of the instrument. So I currently have my voltmeter attached to this test point, and it's set on AC volts. And we see that we're reading approximately 2.6-ish volts, and this should be AC RMS volts. Whereas on the oscilloscope, we're looking at about a 10 volt peak to peak signal, which again is coming out around 2.6 volts RMS. And this is a noise signal, not a sine wave. And so a lot of the signal is going to be well below the 5 volt peak level that is exhibited in the waveform. So if we look at the oscilloscope, it appears to be exactly what we would expect. And we'll move on to the pink noise test. And in order to move from the white noise test to the pink noise test, all we do is put the noise switch in the pink noise position. It's currently in the white noise position. So we're currently assessing test point 10 now, which is really the same point on the boards as test point 9, but we've now moved the noise switch from the white noise position to the pink noise position. We see a slight reduction in noise level to about 1.8, 1.9 volts RMS. And if we look at our oscilloscope, indeed we see the character of the signal changing, and it indeed resembles exactly what we would expect looking at the service manual. So again, the white noise and pink noise functions in this instrument appear to be functioning properly. That's it for board A. We'll now move on to assessing the test points in board B. We're looking at board B2, and we're going to go through some of the test points, starting with test point 1. Test point 1 is looking for the sawtooth signal from VCO 1 and 2, and we're looking for this and the subsequent test point signals as well with the keyboard attached. If we don't have the keyboard attached, we're going to get spurious results. So that's something that's important to recognize. Test point 1 is somewhat cryptic, but it's really delineated by this little ground loop, a very thin loop of PCB trace that encircles a couple of areas here on the board. And first of all, the test point for VCO1 is the junction of C15, R124, and R123, and that is right here. What we're looking for is a descending sawtooth, peaking around 10 volts or so, and coming down about halfway to 0. And we can see that there on the oscilloscope. That's test point 1 for VCO1, descending sawtooth, in this case peaking probably around 12 volts or so. This is the test point for VCO2, and we can see again that descending sawtooth with a similar magnitude and similar frequency. The frequency is set by the coarse frequency sliders for each oscillator, which are set at roughly the midpoint, but that's relatively imprecise, and so that's not going to give us equivalent frequencies there, so we do expect some difference. Now, the second test point 2, is measured off of pin 3 of the integrated circuits, the comparators Z6 in the case of VCO1 and Z3 in the case of VCO2. These are located in this area of the board, Z6 and Z3. So if we come to pin 3, 1, 2, 3,
we see a descending sawtooth coming up to about positive 13 volts and coming down about halfway down to 0, and that's appropriate for test point 2. If we look at the second oscillator and we go to Z3, pin 3, we see roughly the same pattern, and so that suggests to us that the sawtooth is getting through to the it's getting through the exponential converter and is being presented to and coming out of Z3 and Z6. The next test point is the reset pulse. And the reset pulse, again, is not particularly well described in the service manual, but it is the gate for Q15 and Q8. And Q15 and Q8 are in this region of the board, and you'll see a little triangle formed here, and again, an enclosed area with a ground loop, a thin trace, and this is the gate for Q15, which is providing the reset pulse for VCO1, and we can see a reset pulse approximating 15 volts. And the analogous test point for VCO2 is again adjacent to an enclosed loop, and it's right here, and we see that reset pulse for VCO2. And so it appears that VCO1 and 2, insofar as the sawtooth, are working properly, but the next thing to do is to measure pin 7 of both Z3 and Z6. So Z6 again being VCO1, and we see the descending sawtooth in this case. And this sawtooth is imperfect at best. It's a little lazy. It's got a slightly odd waveform, but we can diagnose that later. And then here on VCO2, again, we see a descending sawtooth. And so again, the sawtooth is working perfectly fine. The square wave outputs are measured off of the switches, and the square wave output for VCO1 is measured off of switch 9, and that is right here. And we can see the square wave output is about a 5 volt peak square wave, and the square wave output for VCO2 is measured off of this pin of switch 10. And again, we can see a square wave with a peak of around 5 volts. So it goes from 0 volts to 5 volts. And then the next test point is the sawtooth output. And although we can measure sawtooth out again on switch 9 here at the top for VCO1, and we see an ascending sawtooth with a peak around 6 volts or so. Really a better place to measure this would be from the bus connector here, and we're looking for VCO1 on pin 10. So this is 12, this is 11, and this is 10. And we can see that signal there, the ascending sawtooth wave that is the output from VCO1. And so we know that that is being presented properly at the bus. And pin 11 is the ascending sawtooth for VCO2. We can see that being presented appropriately at the bus. So we know that both we know that the sawtooth is functioning properly. And we also know that the square waves are being produced properly. So the next test point 7, is looking at the LFO triangle wave output. And this is measured off of pin 1 of Z5A. And Z5A is this chip here. It's adjacent to the power connector. And it actually has one of the leads from the PPC connected to it. And so if we connect to this, we can see the triangular wave of the LFO. And so that's functioning perfectly well. The next test point is test point 8. Test point 8 is measured off of Z5 pin 7. Z5 again being here, and pin 7 would be this pin here. And indeed, we see a square wave with a tempo that matches that of the triangular wave that we had just examined. Test point 9 is the sample and hold output, and there are a number of precursors to measuring this signal. First is that the sample and hold noise slider is up. The LFO keyboard slider switch is up in the LFO position. The LFO frequency slider should be up. And then there's another precursor which is not mentioned in the service manual, and that is that the noise gen VCO2 switch 10 needs to be in the up position. Otherwise, this signal will not be measured correctly. It's measured off of pin 1 of the chip Z2 or Z2, which is right here in the board. And the signal should look like this. It should look like a noise signal, and it should be varying from positive to negative in a pseudo-random fashion, somewhere in between, say, maybe about 1.5 to negative 1.5 volts peak to peak. And if you have a signal which is only positive in value, you probably have switch 10 in the incorrect position. So you just simply need to move that, and you should get this voltage signal that varies from positive to negative. And this is modulated in its frequency by the LFO frequency controller. Test point 10 is the ADSR inverter. That is the envelope inverter. And a precursor to measuring this test point is to put all ADSR sliders at 1/2 and then depress any key while measuring. And we should see an inverted envelope off of test point 10. Test point 10 is pin 1 of switch 5, which is located on board B in this position. And we can see that if we measure this without pressing any key, we should have essentially 0 volts. And well, we appear to be floating around positive 1 volts. And if I press a key, we see the attack, the decay, the sustain, and then subsequently the release when I release that key. And so that's functioning perfectly fine. Again, attack, decay, sustain, and then I release the key, and that's the inverted envelope. Perfect. Test point 11 is the trigger processor, and this is measured off of switch 11, pin 3, and that is in this position on the board, board B. And if we measure the voltage at this position, we have essentially minus 7 volts currently. And when we press a key, we see a trigger signal, which is approximately 15 volts or so greater than that. Now, in the service manual, it indicates that this should be starting from a baseline of negative 15 volts. And we seem to be elevated roughly half of that. And we're coming up close to 15 volts. Now, this trigger is still going to work, but it is a little different from what's indicated in the service manual. Test point 1 on board C2 is located at pin 6 of IC Z1. And board C2 actually has the test points indicated on the PCB printed in the foil. And so you can see here, we see the lettering test point 1. And indeed, there's a test point which has been soldered here. And when I put the oscilloscope on this test point, we can see that it's hovering around 1.8 volts or so, maybe 1.6 volts. However, we're supposed to be reading this with the Vcf CV slider up, which is all other sliders down, which is the case. We're supposed to pin a low C on the keyboard. This is low C that I'm holding here. And we should be looking for 0 volts. And indeed, we have 0 volts. One thing that is not mentioned in the service manual is that in order to measure this appropriately, the keyboard CV sample hold mixer switch needs to be in the up position. This is switch number 4, and it is in the up position. We're also directed to pin a high C on the keyboard, and we should be looking for -3 volts, and that's exactly what we have. And keep in mind, again, this is the CD inverter. So the control voltage for the high C is actually a 3-volt signal, but in this case, we're inverting that. So we have -3 volts, 0 volts with a low C, and -3 volts with a high C. The next section of the service manual dealing with test point 2 and test point 3, which are labeled the Vcf output and the VCA output, respectively, contains some errors. So that's not particularly helpful in our case, but regardless, we can set about to correct these. Test point 2, labeled the Vcf output, is indicated on the board right here, and you can see it connects to pin 4 on the module M1, the VCF module. However, if we examine the schematic, we can see that pin 4 is certainly not the output of the VCF. Pin 4 is actually the input for the CV control of the module itself. So if we press a low C, we have roughly 0 volts at test point 2 or pin 4 on the VCF module. And if we play a key, we see a very modest move in the control voltage associated with playing a key. And that is what we would expect. We wouldn't expect to see a waveform on this per se, given the way the synthesizer is currently set up. So test point 2 is certainly not the voltage controlled filter output. Now, test point 3, on the other hand, is connected to pin 10. And test point 3 is labeled here on the board C2, but you can see that by the virtue of this trace, it comes over to pin 10. And we know that pin 10 is indeed the output of the voltage controlled filter module. And when we have the VCF in the VCO1 sawtooth position, and we raise the initial filter frequency slider, we can see that we have an ascending sawtooth, which is exactly what we would expect on the output. This is erroneously illustrated in the service manual, where it suggests that this should be a descending sawtooth wave. So again, this is an error, and it should be both positive and negative with no DC offset, so centered on 0 volts. So since we've determined that test point 3 is erroneously described in the service manual, and it is meant to be the voltage controlled amplifier output, we might want to determine whether or not we can see the voltage controlled amplifier output and determine whether or not it's actually working as it should. So if we examine the schematic, we'll see that the voltage controlled amplifier output is actually on pin 6 of the chip Z2, which is a 3080. Chip Z2, which is the chip that is acting as our voltage controlled amplifier, is actually in this part of the board, and this is a circular integrated circuit, and the pin 1 is labeled 1, 2, 3, 4, 5, 6, going in clockwise orientation. And this is the output of the voltage controlled amplifier. And we can see that we're getting a strong signal, although it does have, appears to have some DC offset, which we can come back and examine later. But suffice to say, that should be giving us something that we should be able to hear, and it's clearly getting the signal from the voltage controlled filter and passing that through the VCA. Test point 4 on the Odyssey is the gate buffer, and this is to be examined in two conditions. One with all the repeat slide switches in the up position. These are the 3 slider switches in the bottom right-hand corner of the keyboard. And this is to be measured off of switch 10, which is the bottom slider switch in the bottom right-hand corner of the keyboard. And so if we connect to this pin on the switch, and there is indeed a test point which has been soldered here, and we press and release a key, which I'm doing now, we see we get a nice square wave. If we press and hold a key, we get a repeating square wave, which is the speed of which is determined by the LFO. And again, if we just press a key, we get this trigger signal for the duration of the key press. Now, if we turn the repeat switch into the auto position, this is the down position, and this is the second switch from the bottom right-hand corner, and we do the same thing, we see that even in the absence of a key press, we're getting that repeating, that auto repeat function, which does not require us to be pressing a key on the keyboard. And so this gate function appears to be working as it should. Test point 5 on board C2 on the Odyssey is the AR output. This is to be measured with the AR attack slider in halfway position, the release slider similarly in halfway position. And the test point is here. We have a post conveniently placed in the appropriate position. And we can see that if we connect to this, we have 0 volts on our oscilloscope. And if we press any key, we should get essentially a AR envelope, which looks like this. We have attack, sustain, and then we release the key, and we have release. So really, the sustain is manual. How long are we pressing that key? And then release. That was a little glitchy. I was wiggling my hand on the keyboard there. But again, you can see this simplified envelope waveform, which is maxing out, peaking around 10 volts, and that's working as it should. Test point 6 on board C2 is the ADSR output, and this is to be measured with ADSR attack slider halfway and the decay slider halfway, sustain and release also halfway. And it's to be measured off of switch 7, which is this switch right here on board C2. And this location, this pin here, is the appropriate position. And we can see that if we connect to this test point, we have essentially 0 volts, maybe a slight negative offset. And by pressing a key, we see the envelope, the attack, decay, sustain, and then releasing the key, we see the release. So again, a full envelope, pressing a key again, attack, decay, sustain, and release. And so the envelope appears to be working as it should.
Well, that's all for today's video. In this video, we've gone through the various test points in the ARP Odyssey and addressed some deficiencies in the service manual. I hope you'll find this approach useful in your servicing of ARP instruments. Again, I'd like to refer you to Synth Chaser at synthchaser.com and his excellent series of videos on ARP instruments. If you've enjoyed this video, please consider sharing it with your friends and subscribing. Thanks for watching. Have a great day.